about transient surge modeling, then there's actually proof of design in the field and gathering data and recording that transient event. In a lot of cases, when I ask customers, oh, you have a pressure transmitter on the system hooked up to SCADA, you know, give me that data in a file so I can look at it. And you end up with a huge data file, and it's very difficult to find the transient event that occurred. Pipe Tech International developed software that has a trigger that they got a patent on, that when you go outside a given pressure envelope, it'll record at a faster rate. So one of the biggest issues out there was the 72-inch conduit, 54-inch conduit. I thought my valve was like 72-inch, but that broke in Puerto Rico. We actually have done several different models on this particular line and looking at valve closing time of 5 minutes. Basically, the valve was set up to close in 30 minutes time. I believe there was a jumper in the motor, stepping motor. Electrician pulled the jumper out and the valve closed in 5 minutes. When the valve closed in 5 minutes, there's upsurge, and it did basically $30 million worth of damage. So that's where your involvement in a project, you really need to understand the whole, risk associated with that project, especially if you have the critical surge components that is going to solve that problem. Yeah, the analysis. Whose fault was it? The owner? Well, human error. Who pulled the jumper out of the electromotor operator? The engineer. The engineer was a good friend of mine, and they're very talented engineers, and they modeled everything about the system. It was repeatable with the transient monitoring data. The contractor installed everything properly, which usually everybody wants to blame the contractor. And most jobs I go to, the contractor calls me up. It's like, I have this pipeline. I hydro tested the line passed, the pressure test, all is well. They turned on the pump, turned off the pump, and now all of a sudden they're telling me my pipeline's leaking. Whose fault is it? Well, the contractor's like, I have a perfect system, everything held. Now my pipe seals are all leaking, and the owner and the engineer aren't going to pay me. Well, the chain of events was they had a pump trip which sent out a negative wave into the piping system and moved the pipe or the seals, which now it's leaking. So whose fault is it? So we look at, recording the data in the event. In this case, the contractor is thrown under the bus. He'll come to us and say, okay, record the transient data that's occurring so we can say, our piping system was installed properly. So you're looking at the piping system back here, and most piping systems, you'll see the pressure rating on the pipe. It's good to 285 psi. But have you ever seen the negative pressure rating of the pipe? What assumption are you making there? And a lot of manufacturers will say, oh, my pipe, we've tested it to a full vacuum, it stayed fine. All right, that was in their laboratory and they pulled a vacuum on it, but it wasn't a transient shock wave traveling through the piping system. So that's where there's a difference of opinion, whereas the piping material and what is an acceptable negative pressure wave. So it's recording the data, and if we look at, pressure gauges in the system, a nice liquid-filled gauge with a pressure snubber on it, is going to buffer out that shock wave that's traveling through the piping system. I had a water system where customers were constantly complaining about the water quality. The water municipality asked me to take a look at their system. They have pump control valves on their pumps, variable speed drives. They think everything's set up properly. He's looking at a gauge. He starts up the pump. You know, it goes from 50 psi to 70 psi, turns off the pump, kind of goes back down to 50 and stays there. He's like, see, I have no water hammer problem. I said, well, you have a really nice gauge, right? It's liquid filled. You have this beautiful pressure snubber on there. Let's just take off your beautiful gauge and put on a non-liquid filled gauge with no pressure snubber. He's like, okay, but I don't have any water hammer problems. That's not my problem. So gauge is on there. It's reading 50 psi. Starts up the pump and it kind of goes to, you know, 95 psi and then settles down at 70. Running it for about 5 minutes. Turn off the pump. Goes from 70 psi to 0. Well, the gauge only went to 0, right? And it stays there for a couple seconds and then comes back up at like 160 psi. And the operator's like, so you're not going to tell anybody about that, are you? I'm like, so sorry. The challenge. It's the sample rate, massive data files, and what actually happened. So how we monitor is we're looking for that upsurge, downsurge, and then change our recording rate. And it'll take a running average that you can record, you know, once a second to once a day, depending on the system. Transient records at up to 100 hertz. And what's interesting, like you had 2 pressure transducers on your system. What we can do is put one transducer at the pump station and or a refinery, and one all the way back at the dock. And what it has is it has a GPS which records for a test procedure, records the location of the test, but also synchronizes the devices from a time step, so you know exactly, you know, in the 100th of a second of when the event occurred, so that we can review the data. The transducer is recording, sending a 0 to 5 volt into the computer system, and just some examples of the data that it's recording. Again, out in the field, fire hydrant, looking at data. We've had several customers that put the systems out in the field and they permanently have them there and recording back in the data, and they go check it once a month. Well, one particular customer, nice, always had beautiful graphs, all is well. One day he opens up his data file and sees these huge transients. It's like, my beautiful system, what in the world's going on? So this is the director of public works, and he starts asking people, hey, you know, what kind of changes have you made into our system? And the purchasing guy's like, oh, we put in these really cool, you know, surge buster special check valves that, you know, totally will take care of water hammer issues. And director of public works is like, we didn't have any water hammer issues. Now we do have a water hammer issue. You bought what the salesperson was selling you, which is destroying our system now. So this is where the proof of design is great in looking at the system and the capturing the data. So again, you know, we look at air valves, making sure the air valves are functioning properly and that the input data into the surge analysis is correct. Of course, valve operator speed in pump, and you can see the wear and tear on the pump. We can also hook this up to a remote location and put in a cellular dialer so we can call up the data remotely. Kind of some general. So again, there's a nice recording of a down surge pump trip oscillating back pressure wave. Oscillations in the system. Looks like they need a pulsation dampener with that graph. And again, a lot of applications. We have one in particular where their control valves are creating, they looked at their pumps, they look at pump trips, they looked at the delivery system. In this case, it was to rail cars and barges. They had no problem, all is well. That was all the input data in the model, and then we started having failures. So we hooked up our computer, and everything would be fine, and then the pump is running, loading a system, nothing should be happening, and then all of a sudden we get this negative transient wave coming through the piping system at like -8, okay? Which isn't supposed to be there. I'm like, you have another valve, you're pulling something else off of the system, where is it? They're like, how do you know we're doing that? I'm like, look at our data. You're doing something else in this system. And again, we found the location. It was the control valves. Again, you think you have 100% of the job finished, but still there's that other piece. This is why everything about the surge analysis in the model, we have to have all the components, all the pumps. So many times I've gone into a pump station and they've got 3 pumps and then a fire pump that's tied into the system. And I'm like, I need those 3 pumps and that fire pump curve because that's the worst case scenario. Because we'll go back after the fact. It's like, oh, well, they only had a problem once a month, and it was once a month that they tested that fire pump. So again, your input data is critical to the model, and again, using a transient monitoring equipment to verify it in the field. At the bottom is our sewage lift station in Kentucky, which is where we split across that recorded the data on the gate valve splitting in half. Six pump trip. Here's a, let's see. So here's I mentioned that project in Kentucky where we had the problem. This is actually the pressure liquid level inside the surge vessels as we're giving energy to that change in velocity. So we were running 2 pumps, we tripped out both pumps, the surge vessel gave energy, kept the line positive, and then accepted and gave energy back and forth. And that was the actual surge vessel that we installed. There's that gate valve again. Up on top of this hill, of course we have high pressures down low, low pressures up high. We hooked up the transient monitoring data. You can see it's very low operating pressure now, but before that, when the line would go to a full cavitation, this whole pipeline would move. So while we're looking at this data, this elderly lady comes out and she's like, what are you doing out in my yard? Like, oh, we're recording data, on this force main. She's like, I don't know what you're doing, but, keep up the good job. I'm like, what are you talking about? She's like, well, up until a couple of weeks ago, we would have, earthquake, several times an hour. And I went and got earthquake insurance, but they wouldn't sell it to me because I'm not on a fault. But the ground would always move, and the windows in my house would rattle, and things would fall off the shelves. And that stopped 2 weeks ago. And I'm like, oh, very interesting. And it's, again, solving that pressure envelope in the system kept that piping from moving under the ground, which unfortunately was moving this lady's house also. We had talked earlier about, the pre-charge pressure in the surge vessel, and to compensate for temperature differentials in the system. So we look at the curve, ambient temperature in this area is 65 psi, and we look at the tolerances for the temperature where the surge vessel should be acting with a temperature differential. If we came out of scope, then our temperature is too low, and we might need to add some nitrogen, in this case, to the precharge pressure. But we can verify, we know how we're supposed to operate and how we're supposed to be giving energy. Again, that was data from the 2-pump trip. Again, kind of before and after, and how the vessel is given energy. And that's actually, we had 2 vessels in this application, and this is you'll see the bladder. It's a butyl bladder. It's polyisobutylene. It's vulcanized and heated together. So pressure, temperature, and then over the bladder material itself, they put a urethane coating to resist it from knives and needles and all the stuff that would be found in a wastewater lift station. So it looks like a big basketball inside there. So this would be to the bottom PVC pipe. PVC pipe, in my opinion, is good to about a -2 psi pressure. What happens to it, both these pictures depict what happens when you have pressure vacuum, pressure vacuum, pressure vacuum. Typically you get the nice long split across the pipe. In this case, the whole piping is shredded. Interesting, you have your wastewater line next to your water line. You know, if you need a good cross connection, there you go. Especially if there's a small leak in that potable water line, you know, you pull a vacuum, turn off that, and you suck some of that good wastewater into your drinking water system. You know, that's where it adds flavor, right? So when in the software, when you go, you know, from a pressure to a vacuum to pressure to a vacuum, the software has a little bit of a problem dealing with that vacuum condition and what's actually going to happen. So this is an actually older version of the model. But you can see it's just gone crazy with that. So you look at the initial data, and then we look at the solution, and you'll see. But in this case, it was rocking back and forth and blew everything apart anyway. So we'll grab node in the pump station. And the bottom line is it goes from 180 psi to a vacuum condition. It's oscillating back and forth, and those crazy pressures were coming somewhere back in the end. Pressure vacuum, pressure vacuum. But, you know, the piping's good to 200, 300 psi max. You know, we're at 800 psi there, so there's no telling when it blew apart. So that's our problem, and then here was with our solution. Now, if you look at how these vessels are placed, it's not a balanced system. If this was an ideal design, I'd have one line coming up and split it between 2 vessels. In this case, if you looked at that data earlier, one vessel is going to give energy different than the other. So it's not a balanced system. This has been in service for about 5 years, and they haven't had any line breaks or problems since. So the initial disturbance, again, is the check valve closing and the shock wave created when those check valves close. Part of the issue in the model and in reality, again, this is a retrofit, is that the dampener and the surge device needs to be as close to the pumps and the check valves as possible. Because between the check valve and the surge vessel, there's no protection in that piping, so that is subjected to that shock wave, as you can see in the initial part of the model. So again, as close to the check valve as possible is to the advantage. So here's our data. Again, that's the check valve closing. With our TP1, we've already recorded that. And you see the cause and effect, and here's the fun part. the marketing part is the before and after. A system in red that now works perfect versus before people's houses were moving and rocking and rolling. Just a little bit more data. It's just going and comparing the flow meter data to what was happening in reality. Here's where what our flow rate did. We were pumping almost 8,000 gallons per minute with 2 pumps. And you can see how it dropped off. Vessels gave energy, then accepted the energy back. Look at the pressure inside the vessel, and then we can also look at the volume change. Again, looking at the volume change, where we went from 510 cubic feet to almost 630 cubic feet, and then taking a step back, we look at the size of the vessel is 1,000 cubic feet, which gives us our safety factor, meaning that the vessel is not emptying completely. If it emptied completely, that bladder that I showed you, it's going to hit the outlet of the grid. Keep hitting the outlet of the grid, you run the risk of it destroying the bladder. This particular model was done, this is a nickel mine in Canada, and they're pumping water straight down the mine shaft. If you look at, this is where the pump is. Elevation is 5,551 feet, and the bottom is at 0. So basically, sea level. The fun part about this was went out there, showed them the model, showed them the problem, and then they're like, okay, we want to show you, the application. And I'm like, well, what do you mean? Like, oh, we'll take you down into the tunnel. And I'm like, it's 5,000 feet into the earth. I'm like, I'm not doing that. Like, oh yeah, come on. So they're giving me these huge boots and this whole outfit and backpack and all this 60 pounds of crap. And I'm thinking to myself, how did I get into actually getting into this elevator and going down a mile into the earth? I'm thinking Chilean miner, Chilean miner, Chilean miner. It's like, wait a minute, Mark with Blako is the one that told me to go look at this project. And I'm like, are you kidding me? So just to give you an example, this would be on the upstream side, looking at the pressure, giving and receiving energy. And as you can see, it's still got a good rock and roll. This case, to date, they have not put in a surge vessel yet. I guess they're waiting for the whole piping to come loose and fall down 5,000 feet into the earth. When it's on World News Tonight, you're like, geez, that's that nickel mine in Canada that they're having problems with, right? We have pumps. We pump a couple miles to the river. On the river, we have a barge that we're loading, okay? Normal control valves operation, the barge is full, the control valve slowly closes off, so there's no surge event. On the barge itself, they have their own valve that on the barge, the barge operator can close the valve. So what was happening is the barge operator would close the valve in 2 seconds. This valve is, let's see, it's a 6-inch valve, and you're thinking to yourself, how does he close the valve in 2 seconds, So the valve is a butterfly valve with a handle, and it's got the lever on it. So what he would do is, he'd hook it with his boot and kick it closed. I'm like, really? Could you just tell them to stop doing that, right? Like, yeah, no, they'd try, and then someone else would come. So the problem is they had, right here's a safety relief valve. And when that relief valve would go off, it would make a big mess because of the process, and, World News Tonight would happen, and, So let's just look at it we'll take the surge vessel out of service and kind of look at the cause and effect of what's happening in the system. So a lot of stress on the piping system.
So you actually needed to have more than one surge suppressor in that system.
It's
one next to the valve.
Yeah, so in reality, the Coast Guard would not let me put in this vessel. All right, so here's my safety relief valve. And the key to this design was that I didn't get to 170 PSI, okay? If I could keep it below 170 PSI, that relief valve's not gonna go off, which means I'm not gonna have to deal with this problem. So, compared to, you're like, well, it looked a lot worse, but So when you look at this particular system, I can flow this way, I can flow this way. What if I'm going in multiple directions? You end up with a very complicated model. And well, you're always trying to look for the worst case scenario. You're pessimistic when you're looking at modeling. Whereas if I can solve it for the worst case scenario, normal operation is all good. So, someone's got to set up that parameter.